Good afternoon, everyone. So we'll start. Just give me a minute. All right. We'll start now. Good afternoon, everyone. So I welcome you all back to the Fluid and Particle Mechanics problem-solving session. So we are in week 5 for this session, and as you all know, the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And the live sessions are handled by myself, Ankara, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, as we all know by now, this is a 12 weeks course, and first few weeks it is dedicated to fluid mechanics, and the later few weeks it is dedicated to particle mechanics. So we have seen introduction to Navier-Stokes equation, tail-required flow rheology, dimensional analysis, and I mean we are almost into dimensional analysis uh, and those things by now. So and few small introduction on particle mechanics as well we have seen. So for books and references we have three books. First one is Unit Operations of Chemical Engineering by McCap Smith, and Fluid Mechanics by Frank M. White, and Introduction to Particle Technology by Martin Rhodes. And for references, we have Coulson and Richardson's Chemical Engineering, John Metcalf Coulson, John Francis Richardson, and Fluid Mechanics by Piyush K. Kundu, and Principles of Colloid and Surface Chemistry by Hemans and Rajagopalan. And last we have Transport Phenomena, Burt Stewart Lightfoot. So we are in week 5, and for week 5 the courses which were covered by the professor in the lecture videos are non-dimensional analysis and concepts of similarity and characterization of particles and motion of particles in a fluid. So these are all the things we have seen in week 5, and yeah, lastly Brownian motion and electrophoresis. So without any wait, we'll start this session now. And yeah, if you have any doubts, please feel free to stop me and ask questions. And yeah, I hope that's all for the announcements. If anything, we will see in between. So I am hoping you people are all submitting the assignments on time as well. Yeah, we'll start the session. So as you mentioned, this week it is more problems are regarding dimensional analysis and concepts of similarity we are going to see, and a few particle characterization problems also we will be seeing. So first one, it is a problem, and we have when tested in water at 20 degrees Celsius flowing at 2 meter per second, an 8 centimeter diameter sphere has a measured drag of 5 Newton. Use this information to make predictions for a 1.5 meter diameter weather balloon moved in sea level standard air under dynamically similar conditions. So what is given? Yeah. What will be the velocity of the balloon if the balloon is dynamically similar to the sphere? Report your answer in meter per second. So there is a one slide in which we explain what are all the similarity, like geometrical similarity, kinematic similarity and dynamic similarity. So in dynamic similarity it is nothing but where forces everything is assumed to be the similar. So here what is given in the question, it is given that when it is tested in a water, so we have two conditions. One is testing in water and it is at a temperature of 20 degrees Celsius, and it is velocity is 2 meter per second, and the sphere diameter is 8 centimeter. So they have a measured drag of 5 Newton. So by using this information we have to predict the velocity for a 1.5 meter diameter weather balloon in the air conditions. So we should be finding and it is given that the balloon is dynamically similar to the sphere. So it satisfies geometrical similarity, it satisfies kinematic similarity, because before that we have those conditions, right? So it is like dynamically similar. So we can use that information to further calculate what will be the velocity of the balloon. So for solution, so condition 1, that is the system 1, is water velocity in, at water the velocity of sphere is 2 meter per second and diameter of that particular sphere is 8 centimeter and drag force is given as 5 Newton. And for the second system we have diameter of ball is given, which is 1.5 meter, and velocity of the balloon is asked, diameter of the balloon, and we are asked to find the velocity of balloon. So similar conditions, so two systems are dynamically similar, and based on that we can take their Reynolds number to be matching. So Reynolds number here is denoted by REP is equal to rho v dp by mu, and here rho is the density of the fluid, v is the velocity, dp is the diameter of the particle in this particular context, and mu is the fluid viscosity. And now we have to, for dynamic similarity, what we have to do is we are just equating the Reynolds number of the sphere and Reynolds number of the balloon, because under similar conditions these are dimensionless numbers, right? So we are taking that condition, and what we are doing, we are just substituting it. So for sphere it is in water, so it is rho water into v sphere into d sphere by mu water, rho v d by mu in water conditions for the sphere, and here it is rho air v balloon d balloon by mu air. This is balloon in air condition. Here it was clearly given that the systems have dynamic similarity. So now what happens is that we can substitute actually v balloon is unknown, so we can keep it and we can take all other things to the other side. So rho water v sphere d sphere by mu water into mu air divided by diameter of the balloon into density of air. So now what happens, V balloon is equal to density of water. So here density of water is 1000 because it is given at 20 degrees Celsius, and V sphere is velocity of sphere is 2 meter per second, and sphere diameter is 8 centimeters. So it is 0.08 meter into viscosity of air. So viscosity of air is 1.8 into 10 power minus 5 kg per meter, meter second. So here it is, we are substituting that value. So divided by mu water. Mu water we can take it as 1 into 10 power minus 3 and into diameter of the balloon is 1.2, no, diameter of balloon is 1.5. So diameter of balloon is 1.5 and density of air it is 1.2. So we just substituted the values in this above formula, and after calculation what we are getting the value as 1.6, because we'll just cross check it once. Yeah, it is right. 1.6 meter per second. So I hope it is clear. Mm, mm, yeah. Now we'll go to question 2. I hope question 1 was clear. Moving on to question 2. What we given is a simple approach to consider the effect of particle shape in fluid particle system is through sphericity. Given a cylinder with a diameter of 1 micrometer and height of 3 micrometer, calculate the sphericity of the particle. So now when we are talking about particle, there are few parameters which are important in context of a solids, like I mean in particle mechanics. So how we define the particle, that is in if it is a fluid we give its properties like density, viscosity. So it can be used to describe the fluid. But when we are talking about particles, we can't describe it directly. Let us consider we have some sugar cubes. Okay, not sugar cubes, but let us take a 5 rupee coin. How will we describe it? We can say its weight, that is one thing, and we can say its size, like this is this much diameter, and we can say its shape. It is like a coin, right? So it is like a cylinder with very less aspect ratio. So those sort of things we can say. Basically what I'm trying to say is whenever we are describing any solids, size of the particle, shape of the particle, density of the particle, those things only play a huge role. So size we can measure it directly if we have a scale, or in a smaller dimensions we have various approaches to measure the size of the particles. For example, we have sieving we do in mechanical operations lab, right? So that gives us the approximate size of those particles. And that density, how can we measure? We can weigh the particles and we can calculate its volume and we can get the density. So that is one of the measure of the particle properties. And I mean one of the important parameters which is describing the particle is its shape. For example, we have a lot of solid substances around us. One may be cube, one may be cylinder, one may be like sphere. So the shape is differing basically. That is the thing. But when we are talking about smaller sized particles, that is in micron sized particles, we cannot describe its shape. So when we cannot describe its shape, we need a sum of factor. So let us consider that when we can describe its shape, in that condition also we need some comparison purpose, right? Like for example, when we are talking about anything, like if how to say, when we are measuring something, we will always have some base values, right? Where in even if you are having a pH testing, we will be having some base to which you will always comparing. So similar to that, whenever we are talking about shape of the particles, we ultimately compare it with the sphere, because in most of the preliminary calculations work done on any systems we take, it would be like considering the particle's shape as a sphere, because spheres are easier to define, right? What do we need to describe the shape of a sphere? We just need its radius or diameter. So with radius or diameter we can say how sphere looks, uh, how it can be. But this is for whole category, I mean single category of spheres. So we can give its radius and we can give its position, we will know how this sphere will be. Like for example, what I'm trying to say is, let us say this is our system. I mean, I'm just trying to explain why shape is important. So we are having one sphere particle at this position and it's of a certain diameter. So with that, two information is sufficient to know where it is located, how it is located. We can imagine that particle. So this same coordinates, let us take, but now instead of sphere, we are given the information that a cube is sitting there. So now if a cube is sitting there, what can we say? We cannot say how it is sitting, right? It can be like a regular position, or it can even be, like crossly sitting. Something like it is not, but you are able to imagine, right, what I'm trying to say. It won't always be sitting straight whenever we are talking about non-spherical particles. I mean, like a cylinder, let us take, it will be easier to imagine. Cylinder can be, if it is here in the same position, it can be sitting like this, or it can even be, sitting this vertical position. So all different uh, ways in which those particles can orient themselves. So these complexities arises basically because of the particle shape. So that again, whenever we are talking about particle shape, we require some base to which we have to compare its shape. Like let us say this, we are traveling on a road. If it is a straight road, I mean, we can say that it is a straight line. But if it is 30-degree deviation, we always, like, we can say it is 30-degree deviated from the normal line. Like that we can say now. So similarly, whenever we are talking about the particle shape, we need some base to which we can compare to. So we take, obviously compare it with the sphere. So we can say that spheres are behaving like this, but the non-spherical shaped particles are behaving like this. So these are in ways in which we can represent the shape of the, not represent, which we can study the shape of the particles. So one parameter which is used to compare different particle shapes to spherical shape is sphericity. So sphericity is that it is defined as the ratio of surface area of the sphere which has the same volume as that of the particle under consideration to the surface area of the particles. So it is said that for if you are taking a different volume of particles, I mean not different volume, different shaped particles, but every shape is having the same volume. That is, we are having a sphere, we have a cube, we have a cylinder. So in this case, what happens is that we have taken sphere, cube and cylinder to be of the same volume, but the one which contains the least surface area would be sphere. So on that basis, only sphericity will be calculated. So it is like, if it is 1, sphericity value of 1 gives us sphere. If it is less than 1, it is all shapes corresponding to, I mean all different shapes will be having certain values. So that only we are going to see now. Now in this particular question, what is asked is, we are asked to consider the effect of particle shape in a fluid systems that, through sphericity parameter. So given a cylinder with a diameter of 1 micrometer and height 3 micrometer, so we have a cylinder. In our case, we need to calculate the sphericity of the cylinder. That is, we need to see how much this particular cylinder will be closer to the sphere in representation. So now, if it is a diameter 1 micrometer and height 3 micrometer, its aspect ratio is 3. So we can imagine that. Now let us go to the solution. So first let us write given. So given, it is mentioned that the particles are cylindrical in shape. and its diameter is given as 1 micrometer. So we are writing diameter of cylinder as 1 micrometer, and second it is height of cylinder is given as 3 micrometer. So now what we are going to do first, we mentioned that sphericity is the ratio of surface area of the sphere having same volume as the particle to the surface area of the particle itself. So for that we need to know a surface area of the particle and surface area of the sphere of same volume. So in order to get the sphere of same volume, we need to know the volume of the particle also. So these three things we need to calculate. So first, volume of cylinder. Cylinder is pi r square h or pi by 4 d square h. And surface area of the cylinder is given as, we have 2 pi rl for the cylinder base, that is pi dh, and we have two circles in the top and bottom, so it gives us pi r square or pi by 4 d square into 2, because we have top as well as the bottom. And third one, we have to compare it with the sphere. So we have a volume of sphere, so it is pi by 6 d cube, that is 4 by 3 pi r square. So for ease of maintaining, I have written everything in diameter instead of radius. And finally, surface area of sphere, it is 4 pi r square or pi d square. So these are the four formula which we are going to use. So now what we are going to do is, first let us find the volume of the cylinder. So volume of cylinder is, what was the formula? Pi by 4 d square h. So pi by 4 into d square into h. D square into h. Okay, d is 1 square h. Alright. So pi by 4 d square h, and okay, after substitution what we are getting is, we are getting, here we haven't changed any of the units, so we are getting 2.355 micrometer cube. Now we are going to find the surface area of the cylinder. So surface area of the cylinder is pi dl plus pi by 4 d square into twice. So we have substituted that, and what is the surface area which we are getting? By 4 plus 3.14 into 3. You can also do the calculation alongside with me. So we can cross check the answer if ever required. So area of the cylinder is 10.99 micrometers square. And now what is the base? The both are having a same volume. So assuming the volume of the sphere is same as the volume of cylinder, we need to calculate the diameter of that sphere. Are you getting my point actually, what I'm trying to say? So it is just that we need to, the base is that cylinder and sphere should have the same volume, so that we can divide the surface area of sphere by the surface area of the cylinder. So what we need to do, we need to assume the volume of sphere is equal to volume of cylinder. So after assuming that, we can get the radius of the sphere. So that sphere volume is equal to the cylinder volume. I hope you are understanding. If you are not understanding, please let me know. So now, based on our assumption, volume of sphere is equal to pi by 6 d cube, and it is d sphere. Again it is d sphere. The volume of sphere is pi by 6 d cube, and after substitution we are getting the, I mean we are not getting this, we are just using the same volume. So d sphere is equal to, now what happens, we are taking everything to the other side, so 2.355 into 6 divided by 3.14 will give us 4.5, and we are taking the cube root of that, which will give us 1.65096. So it is 1.651 micrometer. So now we have to find the area of volume equivalent sphere is pi d square. So here pi d sphere square is equal to 3.14 into this 1.651 square. So that gives us 8.559 micrometer square. So now this, we got the surface area of sphere which has the same volume as that of the cylinder, and we have got the surface area of the cylinder also. So now we are going to substitute it in the sphericity formula. Sphericity is defined as the ratio of surface area of the sphere of the same volume as that of the particle to the surface area of the particle. In this context, the particle is a cylinder. So sphericity now is 8.559 divided by 10.99. So since we have used everywhere in micrometer, we didn't find the need to convert it back, because it is like a dimensionless parameter, so both the surface area gets cancelled. So in this case it doesn't matter if you are converting it to meter or not. So now sphericity is, from this ratio what we are getting it as 0.7788. so this is the sphericity value. So yeah, sphericity is one important term which you will be using it in many areas actually. If you are talking about particle mechanics, the particle shape is very crucial, very important in analyzing the system. Like shape plays a very huge role. Imagine you have a sphere and cube. When you are allowing both in a system and rotating or something, each behavior you can imagine it differently, right? So shape is very important in industrial scale, and because of its importance we need a certain parameters. There are various parameters actually to compare the shape of the particle. Like one such thing is sphericity. There are other things like in two-dimensional, similar to sphericity, we have circularity, and in three-dimensional itself, if we take, we have aspect ratio, we have Cori shape factor. Like lots of shape factors are there to compare, to have some comparison with the spherical shape. So now here in this question we are asked to find the sphericity of the cylinder which has diameter as 1 micrometer and height as 3 micrometer. So now for that, what we need to do find the sphericity is that we need to have the surface area of the sphere which has the same volume as that of the particle, and we need to find the surface area of the particle. Always remember that the surface area of the sphere will be the least. So now for finding out, we found the volume of cylinder. Why are we finding volume of cylinder? We are finding volume of cylinder so that we can assume this volume is equal to the sphere volume and calculate the diameter of that particular sphere which has the same volume as that of this cylinder in our question. So for that reason we are for calculating the volume of cylinder, and after that we are finding the surface area of the cylinder. Later, with the help of the volume of cylinder, we have assumed it to be equal to volume of sphere and calculated the diameter of the sphere accordingly. And later, with this diameter, we have calculated the surface area of the sphere and substituted in the sphericity formula, and we got the answer as 0.7788, or in short 0.78. I hope it is clear. It's clear, right? Yeah. If you have doubts, you can stop actually. Now, let us move on to question 3 actually. Consider a cube with each side of 1 micrometer length. The density of the cube shaped particle is 1000 kg per meter cube. Calculate the specific surface area of the particle. Report your answer in SI units, that is meter square per kg. So what is surface area? Surface area is like area with which the particle is like exposed. I mean the area which is like available for it to make contact with others. So surface area, whenever we talk about surface area, we always say that it is the total area of the area that the surface of the object occupies. So we say the surface, we always say the surface area in meter squares. So there is something else like specific surface area. What is specific surface area? It is the surface area per unit mass of the system. So like we say that whenever the particle size is reduced, the particles will have a large surface area. That is what we say, right? So for example, we can take a eraser or a pencil something. So we will find the surface area of that particular thing and we'll break the system. Now after breaking, what happens? We got two pencils. The volume will be the same, but the surface that is coming in contact will be more now. Why? Because like imagine in 2D. Okay. Now this was the earlier system. So we have four systems. Four sides. Okay. We will be having a certain area. Now what happens is that after breaking we will be having is okay, once again. Okay, let us do one thing. We'll do this thing. This is 2a and height is a. I think in 2 dimension a into b a square plus a square. Okay, now this. Okay, here what happens is that only this is 2 dimension we can't say because the area that is in that we are seeing is the same. But rather what we do, we now take a cube. The cube cube size is a square. Sorry, cube size, let us consider it as a. And now what we do, we know its total surface area will be 6a square. And now let us divide the cube into two cuboids. So since now it will be like a by 2, a by 2. And what is the surface area of cube? It will be like 2 into a by 2 into a plus L into W into H will be a square plus L into H will be again it will be a square by 2. So what happens is that a square by 2 plus a square by 2 plus a square. It will be a square. Okay, I mean a square by 2 plus 2a square. So it gives us equal to 4a square. And this is the surface area of one cuboid. If we take into consideration the other cuboid as well, we will be having one more a square. So previously the surface area was 6a square. Now the surface area is 8a square. 4a square plus 4a square. So it is 8a square. So we are having the same mass. There is no loss of mass or anything. But for the same mass, our surface area is increased by breaking the particles into two. So what does this mean? This means that reduction in the particle size will lead to have more surface area. What is the advantage of more surface area? Surface area is an important property when we are talking about catalysis and all. So it's just that we will have more sites for particle interaction or fluid interaction, whatever. So we will the surface which is exposed to the other environment, environment will be more. So in that case we will have a lot of exposure with the fluid or solid, whichever we want to have contact with. So that is the reason behind it, why we are having a smaller size particles, because smaller size particle will have a larger surface area. Larger surface area will have a larger area, larger area to have the reaction. So that is the thing. So here we saw that the same mass has increased surface area by just dividing the cube into two equal cuboids. So that is the thing. So why we are going with the specific surface area? It offers some base for comparison. Earlier here it is a 6a square per cube. Here it is 8a square for two cuboids. But here in both the cases the mass remains constant. Let us say the initial weight of the cube was 1 kg. So now even after, where is my cursor? Yeah. Even after size reduction, the mass is 1 kg only. So it is 6a square per kg. Now it has increased to 8a square per kg. So that is why we report specific surface area, because it offers us some base to which we can compare it in terms of surface area. So simply if we say 6a square and 8a square, we might not know how the efficiency has increased after size reduction. So that is the reason why we go with a specific surface area. So coming back, how to calculate specific surface area? So now we are given a cube. So for the cube we are given the side length as well. It is 1 micrometer and its density is given as 1000 kg per meter cube. So for specific surface area, what we need it in meter square per kg. So it basically means surface area per unit mass of the particle. So now for this particular cube which has a dimension of 1 micrometer and density of 1000 kg per meter cube, we need to calculate its surface area and we need to calculate its mass. So mass we can calculate from the density. So density is equal to mass by volume. So mass is equal to density into volume. So for this particular cube under our question, we need to calculate its surface area and we need to calculate its volume. So with these two information, we can solve the problem. So let us see how to do that. So first, what is given? Cube side length is given as 1 micrometer and density of cube is given as 1000 kg per meter cube. And now we are calculating the surface area of cube. So surface area of cube, as we saw in the last slide, while doing that division, it is a 6a square. So basically it is cube is having all sides equal and area of a square is a square. So we have 6 surfaces in a cube. So it gives us 6a square. So here again we are now since it is like kg by meter square, we are converting the units to meter square. So surface area is 6a square. So a is 1 micrometer. So that gives us 6 micrometer square. In meter square, how can we write? We can write it as 6 into 10 power minus 12 meter square. Now volume of cube. So V equal to A cube. A here is 1 micrometer. And so 1 micrometer to the power of 3, it is 1 micrometer cube. Sorry. Now mass of cube we need to calculate, and mass is equal to density into volume. So volume is kg by meter cube. Volume is meter cube. Density is kg by meter cube. So volume here we have substituted in micrometer cube and density is in kg per meter cube. So since we cannot do anything with that, what we have done is we have converted micrometer cube into meter cube. So it is 10 power minus 18 meter cube into 10,000 kg by meter cube. And mass of cube, therefore it is m is equal to 10 power minus 15 kg. And specific surface area is, as we mentioned, it is surface area of the cube divided by the mass of that particular cube. So as we saw, like we need some base, so we are taking the mass of the cube. So it is 6 into 10 power minus 12 meter square, that is the surface area, divided by 10 power minus 15 kg. So it is 6000 meters square per kg. So remember this problem. We have one more similar problem which gives us kind of a comparison. I mean, we can see how specific surface area is very important in terms of size. So so basically cube size is given and its density is given, and we are asked to find the surface area of the cube. I mean, we are specific surface area of the cube. So for that, what we need is, we need surface area of the cube divided by the mass of that particular cube particle. So to find mass, we can use volume into density, and to find surface area, we can use 6a square. So after substituting everything, our final answer is this, that is 6000 meters square per kg. So if we have 1 micrometer of cube shaped particles whose density is 1000 kg per meter cube, our specific surface area will be 6000 meters square. Imagine like 1 kg of the particle will be like contained in a small distance, but its surface area now has increased to 6000 meters square. Why? Because its size is very small. That is the reason. So 6000 meters square is a very large surface area, right? So I hope you are able to imagine the cube length is 1 micrometer, and 1 kg of 1 micrometer of cube shaped particles will totally contain 6000 meters square surface area. So that is for question 3. Now we have one more problem. Consider the figure given below and comment on its similarity. So we have a figure and we are given 3 star shaped particle or something, and we have to comment on its similarity. So we are given V1, V2, V3. So what is this is all 3 are star shaped particles, and but the velocity, those components are varying, but so we cannot comment about it. But on looking at it, what we can comment is it is geometrically similar, because we can say that all 3 are looking similar, only variation is its size. So answers, shapes given in the figure are geometrically similar. Now we are going to question 5. For question 5, what we got is kinematic similarity between model and prototype is the similarity of dash. Kinematic similarity between model and prototype is the similarity of dash. Option A, shape. Option B, discharge or motion. Option C, stream. Option D, forces. So when we talk about geometric similarity, it is like the particle shape, those things. And kinematic similarity is next to geometric similarity, which is governing the velocity or the movement of the particle. So in this context, the right answer is option B, that is discharge or motion. So kinematic similarity between model and prototype is the similarity of discharge or motion. And there are three types of similarities exist between the model and prototype. First one, I mean, this is just to give you all these things you would have seen in the theory class by the professor itself. So these are just to give you an idea of and quick recap. Geometric similarity is when the ratio of all corresponding linear dimensions in the model and prototype are equal. So as we saw in the star problem, if we take the ratio of all corresponding linear dimensions in the model and prototype, they will be equal. So we said that it is geometrically similar. Next one is kinematic similarity. Kinematic similarity means similarity of motion between model and prototype. If the ratio of velocity and acceleration at the corresponding points in the model and at the corresponding points in the prototype are the same. So third one, it is it is same means it is having a similar discharge or motion. So that is what we meant by kinematic similarity. Last one, we have dynamic similarity. So the similarity exists when the ratio of forces between model and prototype are equal. So when ratio, it is not ratio, it is ratio of forces between model and prototype are equal. So that is when we say dynamic similarity. This is just to give you an idea. In the previous question, the question was what is kinematic similarity? So it is the similarity between the dynamic, not dynamic, it is discharge or motion. So that is the answer. Now let us go to question 6 actually. A 1/8 scale model of an automobile is to be tested in a wind tunnel at a speed corresponding to the prototype speed of 80 km per hour. Assuming that only inertial and viscous forces are to be modeled, calculate the following. According to the question, which among the following numbers need to be same in order to perform the comparison? So what is given is that we have a model and a prototype whose scale ratio is 1/8. So we are given that the experiment is conducted in a wind tunnel, and a 1/8 scale model of an automobile is to be tested in a wind tunnel at a speed corresponding to the prototype speed of 80 km per hour. Assuming that only inertial and viscous forces are to be modeled, calculate the following. So this is the problem statement based on which we will be calculating the further problems. So in this it is clearly given that assuming that only inertial and viscous forces are to be modeled. So what number relates inertial and viscous force? It is the Reynolds number. Reynolds number is only the ratio of the inertial force to the viscous force. So according to the question, which among the following numbers need to be the same in order to perform the comparison? So option A, it is Reynolds number. Option B, it is Froude number. Option C, it is Weber number. And option D, it is Mach number. So we know that in the question it is given that assuming that only inertial and viscous forces are to be modeled, and based on that we can say that the answer is Reynolds number. Option A is the right answer. And key line, assuming that only inertial and viscous forces are to be modeled. So just to give you an idea what is what, Reynolds number is the ratio of inertial forces to the viscous force. If the objective is to simulate the same balance of inertial and viscous forces, Reynolds number must be there. Second one, it is Froude number. It is the ratio of inertial force to the gravitational force, and it is important in gravity driven important when gravity driven flows are involved, in open channel, ship resistance, those things. And finally, third one we have Weber number. So Weber number is the ratio of inertial forces to the surface tension force relevant in cases involving droplets, bubbles, surface tension effects. Wherever it is coming, we use the Weber number. And at last we have Mach number. Mach number is the ratio of flow velocity to the speed of sound. It is important in compressible problems. So here we use Mach number to define compressibility, compressible flows or not. So Mach number is used in those cases. So it is the ratio of flow velocity to the speed of sound. It is important in compressible flow problems, usually at high speeds at Mach number of greater than 0.3. So in this wind tunnel test, the goal is to model the aerodynamic behavior of a car. Compressibility, gravity and surface tension we are not talking about, and therefore only inertial and viscous forces are to be considered as per the problem. So Reynolds number ensures dynamic similarity between the model and the prototype under the stated assumption. Also in question itself it is clearly mentioned that it is about inertial force to the viscous force, so we can directly go with the Reynolds number effect only. So that is question 6. Now let us go to question 7. In question 7, what should be the wind speed at which model automobile should be tested? Note that the fluid around the automobile and the prototype is same and is air. Report your answer in kilometer per hour. So what is given? What should be the wind speed at which the model automobile should be tested? So we are asking that what is the fluid velocity at which the model automobile should be tested, and the fluid is the same. It is the air in model as well as the prototype. So we should answer in that. Okay, now we'll see how to do that. So scale, it is 1/8 scale it was given. So scale is 1/8, meaning it is a model is prototype is 8 times the model, or model is 1/8 of the prototype. Fluid is the same in model and prototype, and prototype speed is given as 80 km per hour, and we are asked to find the model speed. And what was the unit asked? Report your answer in kilometer per hour. So answer question, it is in kilometer per hour only, and we have to find the velocity of the model. So what was given in the previous question itself, we saw that Reynolds number must be used to ensure or match both the conditions. Reynolds number must be the same under both the conditions, and it is model and prototype. So Reynolds model is equal to Reynolds prototype, and we are just equating between the model and the prototype, and it is rho v d, that is rho model, v model, L model. Rho v d, that d is any characteristic length. So here it is we are given about the scale. So let us consider some characteristic length L model divided by mu model is equal to rho prototype, v prototype, L prototype by mu prototype. So now rho model by mu model is equal to rho prototype by mu prototype. Why? Because it is given that the fluid is the same in model and prototype, and it is air. So all those things, rho by mu gets cancelled. So now we are left with V model into L model equal to V prototype into L prototype. So just we are equating V and L, and in this L model by L prototype ratio is given as 1/8, and we are given the value of V prototype also. So from this we can calculate V model as V prototype into L prototype by L model. So it is V prototype is 80 km per hour, and L prototype by L model is 8, or it is L model by L prototype is 1/8. So anyway, 8 into 8, it is 640 km per hour. So yeah, that is how we did the problem. So what we are doing is we are just equating, or we are just having the dynamic similarity. So we are considering the Reynolds number in the model should be similar to the Reynolds number in the prototype. So Reynolds number is rho v d by mu, and equating the Reynolds number in the model and Reynolds number from the prototype, and we are getting that fluid properties we have cancelled out its density and viscosity, and we are left out with a velocity of the model and length of the model and velocity of prototype and length of the prototype. So we know the scale, so we are using L model and L prototype scale value, and v model, therefore it becomes like 80 into 8, it is 640 kilometer per hour. So that is how we do the problem. And now we got the velocity of the model, so it is 640 kilometer per hour. So now this is question 7. I hope it is clear. Now we found out V model. Now we have to find out drag model. What will be the drag on the prototype? So now instead of model we are given instead of prototype we are given the drag on the model, and we are asked what will be the drag on the prototype, and we are asked to report our answer in newtons. So drag in the model drag is 700 Newton. Now we have to find out what will be the drag in the prototype. So now for that, what we are going to do, we are given that model drag is 700 Newton, and we have to find the prototype drag force, and for that drag is given by half into rho v square into CD into AP, and AP rho and CD remains the same between the model and prototype. CD is again a drag coefficient or a dimensionless parameter. So F model by, we are just taking rho and CD, let it be. We are taking half also, it is a number, it doesn't matter. F model by V square into AP, that is a projected area. So F model by V square model into projected area model equal to F prototype divided by V prototype square into A prototype, projected area prototype. Now we know V model, we know V prototype, we know F model, and AP model and AP prototype can be given as a scale factor, can be given using the scale factor. So now again the same formula. Now what we are going to do, F prototype was asked in the question, so we are keeping F prototype in the one side and we are taking rest all other things to the other side. F model into V prototype square into D prototype, DP prototype square. So instead of AP projected area, we are writing it as diameter square. Projected area is most cases, if it is a spherical particle or anything, we take it as pi r square, and it is pi by 4 d square. So pi by 4 gets cancelled in both sides, so we are left out with only dp square, or it is a surface area, right? So any area, it is a square of the characteristic length. Let us keep it like that. So now it is F prototype equal to this particular form we have got. Now in this we know everything, right? F prototype is equal to F model is 700 Newton into V prototype is, okay, why did I substitute for few alone? Okay, I could have given V prototype also as 80. I don't know why I didn't do that, but yeah, it is 80 square into D prototype square divided by V model square into DP model square. I'll just confirm whether it was. V prototype was 80 km per hour. Again, since it is kilometer per hour is getting cancelled, I haven't converted. Otherwise, if you are having any issues, it is better to go consistently with all the units, because it is in hour, kilometer per hour. It is not a standard SI unit. So F prototype is equal to, we have substituted, and it is 700 into 80 square into dp prototype square by dp model is prototype by 8, 1/8 scale, right? So now after that, 700 into 80 square, d square gets cancelled, divided by 640 square in divided by 64. So what happens, actually it is like let us keep 700 constant. It is 80 into 80. My first 80 is like not looking like 80 anyways. 80 into 80 divided by 640 into 640, and one more 640, it can go that side. So what happens? 8, 1, 0 and 2, 0. Again we can cancel these 2, 0. So 64, 64 gets cancelled, and 8 8s are 64, and the 64 also gets cancelled. So apart from 700, everything else gets cancelled. So F prototype is also equal to 700 Newton. So in this case, prototype is and model has 700 Newton. So it is like, because of dynamic similarity also, it is also getting satisfied. So that is the thing for this particular question. So what we do, we are asked to find the drag force in the prototype. For that we are given in the previous problem itself we have calculated the velocity of the model, prototype, everything we have calculated, and we are now given the model force, which is 700 Newton. So we have considered that F drag is equal to half rho v square CD AP, and here it is F drag is proportional to v square into AP, or F drag is proportional to v square into d square, where d is the characteristic length, and F is proportional to v square A. So F by v square A is equal to, like, between model and prototype is the same, or F by v square d square is same between model and prototype. So d square we can take it using the scale factor, and v square we have calculated for the model. The prototype was given in the question itself. So after that we are substituting everything, and we are getting our final answer as F prototype is equal to 700 Newton, which is basically same as that of the F model. So that is how we do question 8. I hope question 8 is clear to everyone. So now what we are going to do, now we are going to question 9. Alright. What is the power requirement to overcome the wind drag of the prototype automobile? Report your answer in kilowatt. So what is given? What is the power requirement to overcome the wind drag of the prototype automobile? And we are asked to report the answer in kilowatts. So power requirement is given as F drag into V. So here, okay, to find power requirement to overcome the wind drag of the prototype automobile in kilowatt, and solution is power is equal to F into V. So power on the prototype is F prototype into V prototype. So it is, once again, it is like F prototype is power is actually F into V. So we are asked to find the power requirement in the prototype. So we can calculate it using F prototype into V prototype. So F prototype we have calculated it as 700 Newton, and V prototype is given in the question as 80 km per hour, and using that what we can do is 700 into 80 gives us 56,000 Newton kilometer per hour. So basically we want our answer in kilowatts. So for that it is kilowatts is joules per second. Joules is Newton meters. So it should be Newton meter per second or Newton kilometer per second. But for initially we'll write it in Newton meter per second. So 80 it is 1000 kilometers. I mean 1 kilometer is 1000 meters divided by hour it is 3600 seconds. So 1000 by 3600 gives us meter per second. So now after that after substitution and calculation we will be getting it as 15,555 watts. Since in the question it was mentioned that we have to give our answer in kilowatts, what we are doing, we are just calculating the prototype. Oh my goodness, everything is prototype. It is 15 kilowatts, 15.56 kilowatts. So that is how we get our answer, and this is done for question 9. Now we will move to question 10. A simple approach. Okay, what is the time now? 4:10. Okay, I'll give the question actually. Simple approach to consider the effect of particle shape in a fluid particle systems is through sphericity. Consider a cube with each side of 2 micrometer length. Density of this cube shaped particle is 1800 kg per meter cube. Calculate the sphericity of the particle. So now what we are asked? We are asked to find the uh, sphericity of a cube shaped particle whose side length is 2 micrometer length and its density is given as 1800 kg per meter cube. So now let us before you people do the calculation, will take a 5 minutes break or even 4 minutes break. Time now is 4:11. So we'll start again back by 4:15. Yeah. And we'll take a 4 minutes break and we'll start back by 4:15. Thank you. I'll I'll put the question in display. In the meantime, you try solving that. Sorry, I think I kept a wrong. Sorry, I think I kept a wrong thing while leaving. Yeah, we'll start now. So, as mentioned in the question, what we are asked to find is that we have to find the sphericity of the cube-shaped particle, and its size is given as 2 micrometers. Where is my cursor? 2 micrometers. So, we'll see how to do that. So, as mentioned in the previous problems in which we calculated the sphericity for a cylinder shaped particle, what we have to do is we first need to calculate the surface area of the cube, and next we have to find the surface area of the uh, cuboid, not cuboid, sorry, surface area of a sphere which has same volume as that of the cube, and for that reason we need to have the volume of cube which we can equate to the volume of sphere. So these are all the simple steps which we need to follow. And by the way, did anyone try and get any answer? Oh, I see. Oh, sorry. I 0.8. Yeah, it is 0.8 only. Correct answer actually. Hmm. Oops. Sorry. Point 8 is the right answer. We will just see how to do it, so that when if anyone sees from video they can see it later. But point 0.8 is the right answer. So actually side length is given as 2 micrometer. So actually as we have seen, we need to find the volume of cube, and we have to find the surface area of cube, and we have to find the volume of sphere. So volume of cube is given by a cube, and surface area of cube is given by 6a square, and volume of sphere is given by pi by 6d cube, and surface area of sphere is pi d square. So after that we are finding the volume of cube, which is 2 micrometer. So it is 2 to the power of 3, and it is 8 micrometer cube, and surface area of cube is 6a square. So 6 into 2 square, it is 24 micrometer square. So now we are equating this volume of cube to the to be equal to the volume of sphere, and finding the diameter of that sphere. So to find diameter of sphere with same value volume as of cube, actually copied from that slide, that's why. So it is pi by 6 d cube is equal to 8 micrometer cube, and if we take 8 into 6 divided by 3.14 to the whole to the power of 1 by 3, it is 2.4818 micrometer, and area of volume equivalent sphere is pi d square. It is 3.14 into 2.4818 square, it is 19.34 micrometer square, and sphericity, as we all know, is defined as the surface area of sphere of the same volume as that of the particle to the surface area of the particle. And here we are dividing 19.3403 divided by 24, and sphericity is 0.8058. So it is a round off, we can do 0.8 or 0.81, whichever it is fine. So that is for question 10. Now we will see question 11. In question 11, calculate the specific surface area of the particle. Report your units in SI units, that is meter square per kg. So for the previous problem, we are asked to find the specific area of the particle, specific surface area of the particle. So it is meter square per kg. So similar to the one problem which we did back, it is same. So here what we need to do, we need to know the surface area and divide it by the mass of the particle. So here it is cube shaped particle, so its surface area is 6a square, which we have calculated in the last slide as 24 micrometer square. So now we will go to the question. So it is cube side length is given as 2 micrometer and density of cube is 1800 kg per meter cube, and surface area of the cube, which we saw in last slide itself, it is 24 micrometer square. But since we are calculating the specific surface area, we are just using the SI units. So it is 24 into 10 power minus 12 meter square. And volume of cube, it is a cube, it is 8 micrometer cube, and mass of cube is given by mass is equal to volume into density. So volume into density, it is 8 into 1800, and it is micrometer cube. If we convert to meter cube, it will be 10 power minus 18. So 8 into 1800 gives us 14,400 into 10 power minus 8 kg, or 1.44 into 10 power minus 14. That is, we have taken 4 zeros, and it is 1.44 into 10 power minus 14 kg. So that is the mass of the cube. Now surface area of cube is, specific surface area of cube is given by surface area of cube divided by the mass of the cube. So surface area of cube is 24 into 10 power minus 12 meter square, divided by mass of cube, it is 1.44 into 10 power minus 14. It is, I think this is the answer. 24 divided by 1.44 is 16. Yeah, 16 into 10 power square. It is 1666 meters square per kg. So if you remember, there was one problem, same cube problem, wherein we had 1 micrometer size of side length. Okay. Question 3, I guess. Yeah, here it is, cube side length is 1 micrometer and its density is 1000 kg per meter cube. So here we got a surface area as 6000 meters square per kg. Even though density is one factor which is playing here, we can see that with the smaller size we have 6000 meters square, whereas for 2 micrometer sized cube we have a reduced surface area of 1666 meters square per kg. So size of the particle plays a role, that we can understand. But since here we have a density variation also, in the previous problem it was 1000 kg per meter cube. Let us see one more problem in which the density is maintained at 1000 kg per meter cube. So here, just for our understanding, we are just going to see how same sized particles surface area is getting varied. So what if the density is 1000 kg per meter cube? So for that, again cube side length is 2 micrometers and density is, instead of 1800, it is 1000 kg per meter cube. So now specific surface area, if we calculate, it is the same 24 micrometer square, and volume also it is 8 micrometer cube, and mass of cube, it is mass is equal to volume into density. So volume into density, it is 8 micrometer cube into 1000 kg per meter cube. So it is 8000 into 10 power minus 18 kgs, or 8 into 10 power minus 15 kg, and specific surface area we will get by dividing the surface area of cube divided by the mass of the cube. So it is 24 into 10 power minus 12 meter square divided by 8 into 10 power minus 15 kg. So if we do all multiplications and divisions, we will get it as 3000 meters square per kg. So now let us compare this question 12 to the first problem that we saw. In both the cases, density is same, that is 1000 kg per meter cube. But in the first problem, the side length was 1 micrometer, and in this particular problem, the side length is 2 micrometers. So what we got in the first problem, it was 6000 meters square, whereas in this problem we got as 3000 meters square per kg. Both are per kg. So with the reduction in size from 2 micrometer to 1 micrometer, We are also able to see that the surface area is also increased by from 3000 meter square per kg to 6000 meter square per kg. That is the thing which we are able to observe, right? So with increase in size, the surface area will reduce, or in other words, with decrease in size of the particle, the surface area will increase. That is one conclusion. Next is, if we compare question 11 and question 12, the density was varying. So when density was 1660 kgs per meter cube, and here in this problem it is 1000 kg per meter cube. So when density is less, again when density is less, we will be having a higher mass. No, density is less, we will have a lower mass. So here the mass is 14,400 or 1.44, and there it is, mass is low compared to this 8,000 only. So for the same material, like the same particle, for if a particle density is high, its mass will be high. If density is low, mass will be low. So based on that also, we can say that specific surface area is more, even though the surface area is the same between this cube and that cube. When we are talking about specific surface area, the specific surface area is more in this, because the mass of a single particle is low here, because its density is low, mass of a single particle is low. So for 1 kg of the same material, the surface area here will be more, because for getting 1 kg, the number of particles will be also be more here. That is the reason. So since mass of a single particle is low here, the specific surface area is more here. So that is a comparison which I wanted you to see and understand. So that's why similar problem, even though it looks similar, we have included it to just explain you how density and the size of the particle is affecting the specific surface area. So that is for question 12. Now let us move to question 13. In question 13, what we have? These are few conceptual questions only are coming over here with one problem we have. So write the correct SI units of surface area. So when we are talking about surface area, it is meter square. Surface area is simply area. So it is meter square. So surface area is just simply area. So the unit is also simply area. Now if instead of surface area we have a specific surface area, what will be the unit? We all know the unit of specific surface area is meter square per kg. So in question 14, what we are asked to do? We are asked to pick the correct SI unit of specific surface area from the following. So here it is correct SI units. So it is meter square and mass will be in kg. So meter square per kg. So answer is option A, kg by meter square. Option B, meter square. Option C, 1 by meter square. Option D, meter square per second. Option E, none of the above. So we know that specific surface area unit is meter square per kg, but it is not available in any of the options given here. So basically the answer is none of the above, because the USA unit of specific surface area is meter square per kg. It is not available in the options given above. So answer is option E, none of the above. So now let us move to question 15. In question 15, what we are asked to do? We are asked to find the calculate the specific surface area in SI units. Since it is in SI units, we will be calculating it in meter square per kg of a spherical silica particle of 1 micrometer diameter and 2000 kg per meter cube density. So now we are asked to find the specific surface area of a spherical silica particles of 1 micrometer diameter and 2000 kg per meter cube density. So just give me a moment. Is this the same question in your assignment? Just give me a moment. I just want to confirm if this is the same question in assignment or not. If not, I'll change the question. Okay. Okay, since the question is same, what we can do is we can change the shape of the particle actually. We can take cylindrical silica particle of 1 micrometer diameter, and since it is a cube we have to have a height. So let us consider 3 micrometer in height. 2000 kg per meter cube. So I hope it is okay. We'll calculate it now. So it is question 15. Solution. What is given? We are given it is a cylindrical silica particles of 1 micrometer diameter and 3 micrometer height. So it's a cylindrical particle of 1 micrometer diameter and 3 cylindrical silica particle. Okay, so now let us break here. Diameter is equal to 1 micrometer and height is 3 micrometer. Height is equal to 3 micrometer and density rho. So insert close equal to 1000 kg per meter cube. So now we have find surface area of cylinder. And its formula is solution. First we have to find the surface area of cylinder is equal to a cylinder equal to since it is a cylinder we have pi dh first. Where is pi we have, and d cylinder h cylinder pi dh plus pi r square into twice, so it is basically 2 into pi by 4 d spheres, pi by 4 into d cylinder whole square. So d cylinder square. So So in this only we have to substitute. So it is cylinder. So it is basically H cylinder is equal to 3 micrometer. Now we can substitute it. New slide. Question 15, solution. It is 1 micrometer and 3 micrometer. So specific cylinder equal to it is 3.14 into diameter of cylinder is 1 micrometer into 3 micrometer height plus 2 times of 3.14 by 4 into 1 square. So that will give us what it is giving, 3.14 into 3 plus 2 into 3.14 divided by 4. 10.99. It is micrometer square. Insert. Micrometer square. Now what we need to calculate? We need to calculate the volume of cylinder. The cylinder equal to, what is the volume of cylinder? It is pi r square h or pi by 4 d square h. Here into h cylinder. Basically it is 3.14 divided by 4, or we can say 3.14 into 1 square into 3 by 4. We did sphericity calculation for this particular particle actually. That is why it is looking, we are looking familiar. 2.355 and it is micrometer cube. Micrometer cube. Now what we need to do, we need to know the mass of cylinder. So that will give us volume into density. Volume into density will give us mass of cylinder. So volume is 2.355 into 10 power minus 18 into 2000 kg per meter cube. So that gives us into 2000 into 10 power minus 18. So it is 4.71 into 10 power minus 15. It is in kg. So yeah, density, mass is equal to volume into density. So that gives us this. Now we have to find the specific surface area. So specific surface area of cylinder equal to surface area of cylinder by mass of cylinder, which is 10.99 into 10 power minus 12 divided by 4.71. We'll put bracket here. 4.71 into 10 power minus 15. So, minus 15. So we need to divide it. So 10.99 divided by 4.71 into 10 power 3. So it is 2333.33 meter square by kg. So specific surface area of cylinder is therefore 2333 meter square per kg. I hope it is clear. So what we did, we are asked to find the specific surface area of cylindrical silica particle of 1 micrometer diameter and 3 micrometer height and 2000 kg per meter cube density. And so what we did, we first found the we have to find the surface area of cylinder, and we have to find the volume of cylinder, and we have to find the mass of cylinder. So these are the three formula which we need to know. Since it is given a cylindrical particle of diameter 1 micrometer and height 3 micrometer, we are going with that. So surface area of a cylinder is, first cylinder surface area is pi dh plus top and bottom circles. So it is 2 times of pi by 4 d square. So we substituted in that, and we got surface area of cylinder as 10.99 micrometer square, or it is 10.99 into 10 power minus 12 meter square. And volume of cylinder, again it is pi r square h or pi by 4 d square h. So 3.14 into 1 square into 3 by 4. So it is pi by 4 na, that 4 it is. So we are getting 2.355 micrometer cube, or it is 2.355 into 10 power minus 18 meter cube. And mass of cylinder is volume. Mass is equal to volume into density. So volume we calculated, it is 2.355 into 10 power minus 18 into density is 2000, and on substituting we will get it as 4.71 into 10 power minus 15 kg. So specific surface area is surface area of cylinder by mass of a cylinder. So surface area is 10.99 into 10 power minus 12 divided by 4.71 into 10 power minus 15. So after that we will get the final answer as 2333.33 meter square per kg. So that is for question 15. Now we will go to question 16. So since we have been dealing with the Reynolds number problem, let us deal with one problem different from Reynolds number. So first, it is a full scale ship requires 1500 kilowatt to overcome water resistance at 3 knots. If it 1:10 scale model is tested at appropriate speed to maintain Froude number similarity, calculate the power required to tow the model in the testing facility. So now in this question, it is asked to use the Froude number similarity, and scale is given as 1:10. So we'll see what to do. Power in the prototype is 1500 kilowatt and scale ratio is 1:10. Now so it is L prototype by L model is 10. So power is given as force, drag force into velocity, which we saw in one of the problems earlier. So power is equal to F into V. So F drag is half rho V square CDAP. So again, Froude number, what it does, it is inertial force by gravitational force. So Froude number is equal to V by square root of G into L, which basically gives us V is directly proportional to square root of length scale. So now F drag is proportional to V square into L square. L square comes from AP, that is projected area. So one length square, characteristic length scale square. Now power is proportional to power is equal to F into V. So power is proportional to V square L square into V. So it is approximately V cube into L square. So V is proportional to square root of L. So V cube is proportional to L 3 by 2 into L, or it is proportional to L 7 by 2. So this is our ultimate proportionality, that power is proportional to L 7 by 2. That is the only thing which we need to frame from this particular question. So what is given, we are asked to take Froude number similarity in the question itself. So we are given the prototype power as 1500 kilowatts and scale ratio is given as 1:10. So length prototype is equal to 10 times the length model. To calculate power, we take drag force into velocity. So drag force is half rho v square CD into AP. So Froude number, what it states, it is inertial force to the gravitational force. So it is V by root of G into L. So V is proportional to square root of L. So F drag is half rho V square CD AP. So F drag is proportional to V square into L square. So power is V square proportional to V square L square into this particular V. So for this F we put V square L square. For this V we put it directly. So it is V cube into L square. So V is proportional to square root of L. So V cube is proportional to L power 3 by 2. So ultimately we will be getting it as L power 7 by 2 when we take into account these two things. So that is the only thing which we need to clear from this. Then the rest is similar to the normal problems which we do. So now power is proportional to power scaling law under Froude similarity. So power is proportional to L 7 by 2. So power model by power prototype is equal to L model by L prototype, which is to the power of 7 by 2. So now power model by power prototype is 1500 kilowatts and L model by L prototype, which we gave as L prototype by L model is 10. So L model by L prototype is 1 by 10. So 1 by 10 to the power of 7 by 2. So what happens? 1 divided by 10 is 0.1 to the power of 3.5. So it is 3.16 into 10 power minus 4 into 1500 gives us 0.474. Power model is therefore 0.4743 kilowatts, or in normal watts we can write it as 474.3 watts. So even though this doesn't occupy much calculation, we have to get that relation. That is the important problem here. Power is F into V. So here F is directly proportional to V square AP. So AP is a characteristic length square. So V square L square. So we are getting from Froude number, it is V to the power of V proportional to square root of L. So we are substituting here. If we substitute here, V square is L. So it is L cube and one more L will be there. So L 5 plus L 1 by 2. So sorry. No. It is L V square is L. So it becomes L cube into L power 1 by 2. So it is again L 7 by 2 only. Power is proportional to L 7 by 2. L is the characteristic length. So after that we are substituting model and prototype and we are getting the final power as 474.3 watts. That is question 16. Now we'll go to question 17. Question 17 and 18 are kind of theoretical question, just to make you understand that conceptual question. So in what situation is Froude number similarity more appropriate than Reynolds number similarity? Give an example. So in today's problems, we have seen Reynolds number similarity in few cases and Froude's number similarity in few cases. I mean one case. But we have seen the definition of what these numbers mean also in one of the slides. So Reynolds number is the ratio of inertial force to the viscous force, and Froude's number is the ratio of inertial force to the gravitational force, and Weber number is the ratio of inertial force to the surface tension force, and Mach number also we have seen, where it is the ratio of velocity of air, velocity in that particular air to the velocity of sound in medium sound. So it's something like that. So it just defines compressibility. Mach number, I think formula is it wrong. But coming to our particular question, it is comparing Froude number similarity and Reynolds number similarity. So when it will be more appropriate to go with Froude number similarity. So we can say that since Reynolds number is inertial to viscous force and Froude number is inertial to gravitational force, whenever we are dealing with anything more prominent with gravitational flow, we can go with Froude number. Rest other cases we need to go with Reynolds number whenever we are talking about viscous situations. So answer is Froude number similarity is more appropriate when gravitational forces dominate the flow behavior. This is what we have seen. Froude number is the ratio of inertial force to viscous force. So it is more appropriate when gravitational forces dominate the flow behavior. Froude number is defined as Froude number is equal to V by root of GL, where V is the velocity, G is the acceleration due to gravity, gravitational acceleration, and L is the characteristic length. In flows where gravity significantly affects the motion, such as in free surface flows, wave formation, or floating objects, preserving Froude number ensures kinematic and dynamic similarity. So in those cases we use Froude number similarity. And examples where we are asked to give an example. So examples where Froude number similarity is more appropriate: ship resistance and wave generation in water, flow over spillways or open channels, river modeling or dam break analysis, and motion of floating bodies, those things, boats, buoys, everything. So this is the case. These are the cases in which we use Froude number similarity, because it is more appropriate in these cases than using Reynolds number similarity. So coming to last question for today's session, a model is tested in different fluid than the prototype. Example, air instead of water. What challenges arise in maintaining similarity and how can they be addressed? So whenever we are using a different fluid in the model and the prototype, there are some issues which will be occurring, and the question is what are all some general challenges and how can we address? When a model is tested in a different fluid than the prototype, it becomes difficult to simultaneously match all similarity criteria, especially the Reynolds number and Froude's number, because we have to ensure geometric, kinematic, and dynamic similarity. It is kind of difficult to address all similarity criteria when we are dealing with the Reynolds number or Froude number, because fluid property varies, density varies, viscosity varies, and Reynolds number depends on both fluid and the geometry, because it is rho v d by mu, where d is the characteristic length. So it depends on fluid properties as well as the geometrical properties. We may not be able to achieve the same Reynolds number without adjusting either the fluid velocity, model size, or using a different fluid altogether. So like to get the same Reynolds numbers, similar things, we have to adjust the fluid velocity, Reynolds model size, characteristic length. These all things should be addressed. We should be able to maintain it consistently. So challenges are Reynolds number mismatch may lead to incorrect scaling of viscous effects. So if there are some mismatches, it might lead to incorrect scaling of the viscous effects. And Froude number mismatch may again lead to incorrect scaling of the gravitational effects or wave effects. It is often physically impractical to match both, especially in wind tunnels or water tanks. So depending on which fluid, what are all the dominating factors we need to consider. So these are few challenges. How can we address those challenges? Change the fluid to one with more favorable properties, like where we can easily compare both, and use a pressurized or heated test environments to manipulate fluid properties. Use CFD to correct or account for mismatched similarity. So by using CFD, we can get a proper solution with what we are trying to achieve. So, and apply correction factors based on empirical data or any validated models. So by using them, we can get some ideas on what to do. So yeah, these are just, this won't come as a question actually, question 18 especially, but just to give you an idea of what it is. Similarly, question 7 also, like just to give you an idea. So Yeah, that's of problems only are will be asked in problems are only asked in assignments. So most of the problems we solved in today's class is similar to assignment problems only. So I request everyone to like submit your assignments on time, because assignments also carry certain weightage in your final exam. So that's it for today's session. If you have any doubts, we can discuss, or yeah, we can leave the session. Yeah, thank you for attending today's session. We'll meet again next week at the same time, 3 p.m. to 5 p.m. And I'll close the session. Yeah, thank you.